Hello, I'm John Doherty and I'm the author of PEST. The purpose of this video is to discuss some of the functionality available through PEST and through the PEST suite, and to describe the place that PEST takes in decision support modeling, for that is the context in which PEST and its support software is generally most used. Before we talk about PEST and its accompanying software, I want to say a few words about decision support modeling. PEST is normally used to support environmental decision making, the management of environmental systems. These can be groundwater systems, surface water systems, systems which involve representation of different land uses, and maybe optimization of those land uses to support best management of a system. Now, whenever we make a decision, fundamental to the decision-making process must be the assessment of what can go wrong if I adopt a certain course of management action. It follows then that to the extent that we use modeling, numerical simulation, as a device to allow us to support decision making, that simulation process must be targeted at assessing risk. And risk is loosely defined as the cost of something going wrong times the probability of something going wrong. Once I have assessed the risk associated with different courses of management action, I can choose the course of management action that is optimal, and what is optimal depends on the context. But whatever the context, knowing what can go wrong if I adopt a certain course of management action is fundamental to supporting the decision-making process. It follows then that if modeling simulation is used as a device for decision support, it must be used in a way that focuses on the behavior of a system if we take certain courses of management action and inquires into what are the range of possibilities that will emerge from that course of management action. When we're looking at environmental systems, particularly groundwater systems, the uncertainties associated with decision-critical model predictions may be very high. The modeling process needs to embrace that. The modeling process also must attempt to reduce the uncertainties of those predictions as much as it can through assimilation of information that's available to us at the time of making the decision. Now, that information may be available through site characterization studies. It may be available through measurements of the historical behavior of the system. The decision support modeling process must then be more than just a process of numerical simulation. It must be a process of assimilating all information that's pertinent to predictions of management interest in order to quantify the uncertainties of those predictions, in order to reduce those uncertainties as much as we can, given the information that's available to us. If we then accept this as the place of decision support modeling, we must accept that simulation, modeling itself, is only part of this process. The other part requires software just as complex, just as important as the simulator itself. It requires software such as PEST that can dance with the simulator. That is what I like to call a model dancing partner. Software that's used in conjunction with the model to assimilate, process data using the model in order to quantify the uncertainties of predictions of management interest and reduce those uncertainties as much as we can, this then being fundamental to the making of decisions regarding environmental management. And let me just say a few words about quantification of model predictive uncertainty. If we talk about uncertainty, we have to talk about Bayes' equation. Bayes' equation is, well, the last word on history matching. And history matching is an important component of decision support modelling, because that is one way to assimilate certain data that can allow us to reduce the uncertainties of decision critical model predictions. Bayes' equation says that we start off, before we do any history matching, with uncertainty. And that uncertainty is expressed by this prior probability distribution, this term on the far right of Bayes' equation. This is the outcome of expert knowledge and site characterization. After we've characterized a site, measured system properties at a number of locations, there's still plenty of uncertainty of what the properties are at other locations. So the prior probability distribution expresses uncertainties that are forthcoming from expert knowledge and site characterization. These are the uncertainties that exist before we do any history matching. That's why this is called the prior probability distribution. Then we do the history matching. And Bayes' equation says the outcome of history matching is a so-called posterior probability distribution of parameters and predictions that a decision support model is required to make. Bayes' equation says that history matching does not eliminate predictive uncertainty. History matching at best can reduce the uncertainties of some decision critical model predictions, but those uncertainties may still be high. So Bayes' equation says that we start with uncertainty, the prior probability distribution, and we finish with uncertainty, the posterior probability distribution. You may well ask then where does the calibrated model fit into this? The calibrated model often forms the cornerstone of decision support modelling, but where does it fit into Bayes' equation? If we are going to replace a probability distribution with a unique parameter field, which calibration seeks, what right do we have to do that? Well, the answer is, sadly, that uniqueness, calibration, doesn't really fit into Bayes' equation. It's a numerical convenience, but it is an artificiality. It is a convenience, and in some circumstances can assist the decision support modelling process by allowing us to do things such as test the conceptual basis of our model, but it must not be seen as the final deliverable of the decision support model, that is, a model calibrated with a unique parameter field. But if we are going to take a probability distribution and replace it with a unique parameter field, and if we do that the right way, what we should produce is a parameter set that allows us to make predictions of minimum error variance. That is, we should be able to make predictions that lie within the center of their posterior probability distribution. However, if we're building a model that's going to assist us in supporting the decision-making process, normally it's because we are about to embark on some environmental management strategy, and we're doing that because there's some bad things, I'm going to call them bad things, that we would like to avoid. That is the purpose of environmental management, to avoid bad things happening. And it's obvious that knowing that we can make predictions that are in the center of a posterior probability distribution is nice. It's not nice enough. We need to know the width of that posterior probability distribution if indeed we are going to assess risk, if indeed we are going to find out that there may still be a finite probability of a bad thing happening if we undertake a certain course of management action. We may still undertake that course of management action, but we need to be fully acquainted with the risks that we're taking. Hence, modelling for decision support requires that risks be calculated, that uncertainty be quantified. It requires recognition of a few fundamental premises. In particular, decision support modelling requires recognition of the fact that a model can never tell us what will happen in the future. It can only tell us what will not happen in the future. It requires recognition of the fact that in environmental systems, parameter non-uniqueness is generally rife, particularly as it pertains to groundwater modelling. The medium through which water flows beneath the surface is heterogeneous at every scale, and we do not know the properties from place to place, but we know something about those properties from site characterization. Uncertainties may be reduced through history matching, but there will often be many different sets of parameters which can allow us to fit a calibration data set. Hence, decision support modelling requires recognition that parameter non-uniqueness prevails and that the uncertainties of many decision-critical model predictions will be uncertain because of parameter non-uniqueness. A lot of their uncertainty will be based on the fact that there are a lot of ways to fit a calibration data set. What also must be recognised is that given the important role played by uncertainty analysis in decision support modelling, given the fact that parameter non-uniqueness is often a large contributor to the uncertainties of decision-critical model predictions, we must endow a model, particularly a groundwater model, with a lot of parameters, not because they can be estimated uniquely, but precisely because they cannot be estimated uniquely, because unless they're represented in the model, how can we quantify the uncertainties of decision-critical model predictions? How can we assess the risks associated with certain courses of management action? This is the context in which PEST is designed to operate in order to play its role as a dancing partner to a simulator in decision support modelling. So now let's spend just a few moments looking at what makes a good model dancing partner. Two things are fundamental to this. The first is that the dancing partner, such as PEST, has a non-intrusive interface with the model. The second is that it has the ability to undertake model runs in parallel. The history matching process, the uncertainty quantification process, often requires that many model runs be undertaken. These should be undertaken in parallel so that they can be done in a finite amount of time and make maximum use of available computing resources, all of which give us many opportunities for parallelization these days. So, here's a model, a simulator. We're assuming that the model has input files, one or a number of input files, one or a number of output files. We'll also assume that these are text files, not binary files. A model can have binary input and output files, but the ones that PEST interacts with a model through need to be text files. So, the model also must be capable of being run using a system command. That is, PEST must be able to use a command, the same command that you would use if you type the model's name into a command line box. Such a command is used by PEST to inform the operating system that it must run the model. So these are the fundamental requirements. Text input and output files, at least the one that PEST uses to interact with the model, and the ability to run the model using a system command. The model cannot be concealed behind a graphical user interface in a way that it cannot be run on its own. So a user then prepares for each model input file a template of that input file. This identifies the places on the input file where model parameters are written. It can be as complicated as you like, and a model can use thousands of parameters. A template file informs PEST where it must write the values of parameters that the model must use on any particular model run. Once the model is run, PEST must be informed through instruction files that are prepared by the user of what numbers must be read from model output files, presumably to be compared with field measurements, so that parameters can be adjusted through repeated model runs in order to minimize mismatch between model outputs and corresponding field measurements. The model itself can be as complicated as you like. In most cases, a simulator will be accompanied by one or a number of preprocessors. This gives us flexibility in the way we define model parameters. A simulator will often be accompanied by one or a number of post-processors. This allows us to perform tasks such as temporal and spatial interpolation from model output times and locations to the times and locations at which field measurements were made. Or we may wish to calibrate multiple models simultaneously. There is no limit to the complexity of the model, which may include one or a number of simulators calibrated simultaneously, and that one or a number of simulators encapsulated in a batch or script file can have as many input files as you like, can write to as many output files as you like. We just require that template files exist for each of the model input files, and that instruction files have been prepared corresponding to each of the model output files. The second important requirement, as we have just mentioned, of a model dancing partner is the ability to parallelize model runs. PEST and other dancing partners that come with the PEST suite use the manager-agent philosophy. So here is PEST, for example, performing its role in model calibration or uncertainty analysis. Inside this dancing partner program is the algorithm which does the history matching. Also is a run manager. The actual model runs are carried out by so-called agents. These agents communicate with the manager, which holds the algorithm for which the program was built, that is the inversion algorithm, the uncertainty quantification algorithm, and code that conducts model runs. A message is sent to each one of these agents whenever a model run is required, sent to one of those agents. The parameter sets that the agent must use are provided to it through TCP/IP. The model is run by the agent, and then the agent sends back the outputs from the model which PEST or another program in the PEST suite requires in order to perform its history matching job. These agents can reside on the same computer as the manager. They can reside on different computers in an office environment connected by a network. They can reside on other nodes of a high-performance computing cluster. They can reside on other virtual machines on a computing cloud. The principle of operation in each one of those contexts is exactly the same. So now let's turn our attention to what PEST actually does. PEST is at the center of the PEST suite. As I said a moment ago, it is not the only dancing partner supplied with the PEST suite, but it was the original member of the PEST suite. Originally, PEST was written to undertake automatic calibration in a setting where the inverse problem is well posed. And as stated already, it was written to do this in a model-independent way. That is, it was written originally and still does interact with a model through the model's own input and output files. However, since the time at which it was originally written, its inversion algorithm has become considerably more complicated than it first was. PEST has 4 modes of operation, these being those that are listed in this slide. If run in parameter estimation mode, it does what it was originally written to do, that is, to solve a well-posed inverse problem. Complementary to that, it can undertake predictive uncertainty analysis for a problem that is well posed or reasonably well posed. That is, it can maximize or minimize the value of a model prediction subject to the constraint that a good match is maintained between model outputs and the calibration dataset. If run in regularization mode, it can solve highly ill-posed inverse problems using a variety of regularization devices to ensure that the solution to that problem is of minimum error variance. And if run in Pareto mode, it can also accommodate the use of many parameters and problems which are ill-posed. When run in Pareto mode, it plays one objective against another. For example, it may play maintenance of regularization constraints against attaining a good fit with a calibration dataset, or it may be used to undertake direct predictive hypothesis testing where we play maintenance of a good fit with the calibration dataset against achievement of a certain user-specified prediction. Some specifications are listed in this table. PEST can estimate thousands of parameters using tens of thousands of observations that comprise a calibration dataset. Weights assigned to those observations are user-specified, or covariance matrices can be used instead of weights. Regularization devices include Tikhonov, singular value decomposition, and LSQR. Sensitivities or derivatives that underpin the gradient-based methods that PEST employs to implement regularization. These sensitivities can be supplied by the model itself if the model can calculate them, or, as in most cases, PEST can calculate sensitivities using finite parameter differences. In doing so, it can use 2, 3, or 5-point stencils for the parameters. PEST has a reasonably high tolerance for granularity of model outputs, born perhaps of numerical difficulties that the simulator encounters in solving its system state equations. In solving an inverse problem, PEST keeps a comprehensive record of everything it does and can parallelize model runs in solution of that inverse problem, but also, if you want to, it doesn't have to solve an inverse problem at all. It can simply undertake a whole lot of model runs in parallel so that you can look at the outcomes of those model runs. This may be useful in sensitivity or uncertainty analysis. There's a lot of sophistication in the inversion algorithm that PEST employs, and it goes to a lot of trouble to make that process efficient, hopefully reducing the number of model runs required for solution of the inverse problem as much as possible. Devices that it uses includes some of the ones that you see here: sensitivity reuse, simultaneous parameter increments, superparameters, and construction of a pseudo-sensitivity matrix from random parameter realizations. Bounds can be imposed on parameters. Parameters can be tied or fixed. Files can be transferred between the run manager and various agents. This can promote a high degree of efficiency as parameters change and initial model conditions change. PEST can use a simple model and a complex model in conjunction with each other to increase the efficiency of the inversion process. It can transform parameters so that PEST can estimate transform parameters while the model can actually use its native parameters. A PEST run can be stopped and restarted at the same place at which it was stopped. And there's many other little things that go into making the PEST algorithm as useful and efficient as possible. PEST requires 3 types of input file. We've mentioned template and instruction files. The third type is the PEST control file. This is the file that tells PEST what to do and specifies variables which govern the implementation of its inversion algorithm. PEST is supplied as a set of Windows executables. Alternatively, source code and Unix makefiles can also be supplied so that it can be compiled for use on a Linux cluster, for example. As I said before, PEST isn't the only dancing partner in the PEST suite. Supplied with the PEST suite are a couple of global optimizers, the CMAES and SCE global optimizers. A program called JACTest, which can test the integrity of finite difference derivatives calculation in order to see whether the model is numerically well behaved or not. Realization space inversion, well, that's a little bit like an ensemble smoother, an efficient way of sampling the posterior probability distribution of parameters, and a generalized agent to assist in undertaking model runs in parallel. PEST is extensively documented. Every program that I've just shown you and all support software, which we'll talk about shortly, is documented in a comprehensive suite of manuals. And I should draw your attention to another suite of programs called the PEST++ suite. These are interoperable with PEST. They read a PEST control file. They use template and instruction files. They can be downloaded from this site. Some of the members of the PEST++ suite duplicate what PEST does. Others go beyond and look at things like optimization under uncertainty or an advanced ensemble smoother. As stated, they can be downloaded from this site. PEST is accompanied by 3 suites of utility support programs. The first suite is supplied with PEST itself. The other suites are supplied separately, and I'll talk about those shortly. All of these utilities are like PEST, they're discrete programs. Windows executables are downloadable with PEST. The source code can also be provided so that you can compile them yourself for use on any system. The utilities supplied with PEST can be divided into a number of categories on the basis of the jobs that they do to support the use of PEST. The categories are set out in this table. Now let me say a few words about each of them. The first set of tasks are provision of assistance in construction, manipulation, editing and checking of PEST input datasets. PEST input datasets can become complicated if an inversion process itself is complicated. If there are many parameters that require processing, many outputs that require processing, if a number of models are being calibrated simultaneously, all of these add to the complexity of the inversion process and of the files that are required to implement that inversion process. Various utilities provide assistance in building a PEST control file, in building instruction files, in providing weights to observations, in reconfiguring weights to balance the contribution to the objective function by different observation groups. Some utilities will automate the addition of tick-and-off regularization to a PEST control file. Others will build new PEST control files from old PEST control files but containing optimized parameters. Still other utilities will check the entirety of a PEST input dataset for correctness and consistency. Another function performed by the utilities is manipulation of parameter sensitivities. If these are calculated using finite parameter differencing, then calculation of sensitivities in a highly parameterized context may take a lot of model runs to implement. Hence, anything that can be done to save having to recompute sensitivities or to compute new sensitivities from old sensitivities can ease the computational burden of doing things with PEST enormously. Hence, a number of utilities are dedicated to manipulating files, so-called JCO files. JCO stands for Jacobian. A Jacobian matrix is a sensitivity matrix. So various utilities can build one JCO file from another, can extract parts of a JCO file to build another, can build a single JCO file from multiple JCO files, can build a new JCO file for a new PEST input dataset, provided certain conditions are met, if that new PEST input dataset is derived from an old PEST input dataset. Another role played by PEST utilities is to act as model pre- and post-processors. Hence, these utilities will comprise part of the batch or script file run by PEST as the model which PEST is calibrating. As a preprocessor, these utilities can transform parameters so that the parameters that PEST sees can be slightly different from those which the model sees. Other utilities can post-process model outputs, so before matching those outputs with field data. A very important function performed by some utilities is that of linear, parameter and predictive uncertainty analysis. Considerable use can be made of parameter sensitivities encapsulated in a JCO file. These utilities can calculate the prior and posterior uncertainties of important model predictions under an assumption of linearity, model linearity. They can calculate the reduction of uncertainty of a model prediction accrued by the use of different types of data in the calibration dataset. And the operation of linear analysis is such that you don't even have to have acquired certain data to be able to calculate the ability of that data to reduce the uncertainties of decision-critical predictions. Linear analysis can be used to compute parameter identifiability, a number between 0 and 1, which tells you how much the calibration dataset has the ability to inform or not inform every parameter that comprises part of the parameter set that PEST is trying to estimate. Linear analysis based on sensitivities can be used to explore the reasons for model-to-measurement misfit. They can be used to track flow of information from observations to parameters. They can be used to draw graphs like this. The back row is the contribution made by different types of model parameters to the uncertainty of a critical model prediction. The back row is prior to history matching. The front row is parameter contributions to the uncertainty of that same prediction after history matching. So one can see at a glance what parameters are causing most uncertainty and how much that uncertainty is reduced through the history matching process. Here's a graph of parameter identifiability as calculated using one of the utilities, the linear analysis utilities. Here is a map of uncertainty reduction of all the parameters in a certain layer of a groundwater model. Using linear analysis implemented relatively easily and quickly, using these linear analysis utilities supplied with PEST, one can see at a glance where a calibration dataset has reduced the uncertainties of parameters employed by a model and where it has failed to reduce the uncertainties of those parameters due to lack of information density or because of excessive noise that may accompany, or measurement noise that may accompany, certain parts of the calibration dataset. Other roles played by the utilities include not linear but nonlinear uncertainty, parameter and predictive uncertainty analysis. So some utilities can be used to generate random parameter sets. We can sample the prior parameter probability distribution. We can sample a linear approximation to the posterior parameter probability distribution. Other utilities can set up PEST so that it can then adjust those samples of a linear approximation to the posterior parameter probability distribution such that those parameters actually become samples of the true posterior parameter probability distribution. Hence, they can all calibrate the model just as well as the original parameter set that was derived through the inversion process. Samples of the posterior parameter probability distribution attained in this way can then be used to implement Monte Carlo analysis of predictions of management interest. Another new addition to the PEST suite undertakes data space inversion. This is a method of posterior predictive uncertainty analysis that can be implemented where model run times are very long. The uncertainty of a prediction can be explored without having to actually ascertain the uncertainty of parameters to which that prediction is sensitive. Still, other utilities can be used to analyze the outcomes of a PEST run so that we can look, for example, at influence statistics, the way different observations influence the estimation of parameters. Advice can be given on whether PEST settings are optimal or not, given what PEST has recorded on its run record file. Weighting strategies can be adjusted on the fly based on the outcomes of a previous PEST run. The integrity of finite difference derivatives can be assessed. This may be important if it is suspected that PEST behavior is not as good as it should be because of malperformance of the model that PEST is being used to calibrate. Then there are two other completely different sets of utilities that can also be downloaded from the PEST website. The first of these suites were written to facilitate the use of PEST in groundwater model calibration. Like all software we've talked about so far in this video, the utilities which comprise this suite comprise discrete programs for which Windows executables are provided. Alternatively, or as well, source code can be provided so that you can compile them for use on a Linux system. Like all other programs we've discussed so far, documentation is extensive. The groundwater utilities serve a number of purposes. They're all built for use, or mostly built for use, in a highly parameterized world. The benefits of highly parameterized inversion have been briefly discussed in this video and were discussed extensively in other videos. Highly parameterized inversion provides a better guarantee of minimum error variance solution to the inverse problem of model calibration than use of more parsimonious parameter sets. Also, they provide more robust estimates of predictive uncertainty. Don't forget, it's the parameters that you cannot estimate that are just as important as those that you can when it comes to quantifying the uncertainties of some decision-critical predictions. The more parameters that we have, the more flexible does the inversion process become, the more robust it becomes, the more satisfying it becomes because heterogeneity can find itself rather than having to be placed in positions preconceived by the user. Of course, this only happens when regularization is properly implemented, and part of the role of these utilities is to assist in the implementation of Tikhonov regularization in a variety of groundwater modeling contexts. Not only can these utilities be of use in the parameterization of a model, in the construction of covariance matrices that assist in Tikhonov regularization, and in pre- and post-calibration uncertainty analysis. Some of them have been built for use in processing model outputs and in formulating creative multi-component objective functions. As is discussed in other videos, formulation of an objective function that is minimized through the inversion process is often a critical component of attaining a minimum error variance solution to an inverse problem. Hence, these utilities can be used to not just undertake spatial and temporal interpolation from model outputs to the sites and locations of measurements. They can also be used in processing model outputs, for example, by undertaking differences, so that processed model outputs can be matched to processed observations. As explained elsewhere, this can often protect the inversion process from calibration-induced bias. Still, other utilities can allow us to form penalty functions that can facilitate user involvement in the inversion process, providing yet another mechanism for attainment of a minimum error variance solution to the inverse problem. Some of the utilities were written to expedite use of PEST with specific models, for example, all members of the ModFlow suite. Some of them are more general and can be used with any type of model and have been used with to facilitate the use of PEST with all the models listed in this table. Extensive support is provided for pilot point parameterization, particularly in contexts of unstructured grids. Hence, pilot point parameterization can be used in calibration of ModFlow USG, ModFlow 6, FeeFlow, and other models. Not only do these utilities allow or facilitate spatial interpolation from the sites of pilot points to the nodes of finite difference or finite element grids, they also can help in the construction of covariance matrices used for regularization and for uncertainty analysis, so that geostatistical methods can be blended with pilot points to optimize the construction of suitable regularization and uncertainty analysis devices applied to pilot points. Here's an example. This is a ModFlow USG model focused on a mining site. This model was actually built by a colleague of mine, and this is coloured according to the log of hydraulic conductivity estimated through the inversion process. 3 sets of pilot points were employed, all emplaced and regularized using utilities supplied with the groundwater utility suite provided with PEST. 3D pilot points near the pit, regional 2-dimensional spatially variable pilot points, and pilot points arranged along the different faults which intersected the pit. Here they are all together, and here is the log of the hydraulic conductivity field that emerged from the inversion process. Some utilities were written really without PEST in mind, just to perform functions that are useful but not necessarily built to facilitate the use of PEST with any particular model. For example, some utilities were built just simply to read output files produced by commonly used models. Some were written to read files, input files for these same models, and reformulate their construction in other file types that can then be imported into visualization or GIS packages for display. So, some of the utilities have little to do with the use of PEST. Many of the others were designed specifically to enhance the use of PEST with one or a number of particular groundwater models. And finally, let me discuss the surface water utility suite that, like the groundwater utility suite, can be downloaded from the PEST website. Like all the other software that I've discussed in this video, this suite is comprised of a set of discrete programs for which Windows executables are provided, but source code is also provided so that they can be compiled for use on a Linux system. And, as always, documentation is extensive. The Surface Water Suite was built to facilitate the use of PEST, as the name suggests, in calibration of complex surface water models. Like the Groundwater Suite, they were built with highly parameterized inversion in mind. And in my opinion, if through the adoption of highly parameterized inverse methods, calibration of surface water and land use models could achieve a lot more than it is achieving today in a lot of situations. For example, if we've got 3 watersheds here, conventional wisdom says calibrate them sequentially, starting from the top and working down. The trouble with that is that it doesn't make use of information that's available to reduce the uncertainties of parameters that are estimated through the history matching process. There will be non-uniqueness in estimation of parameters in each watershed, hence uncertainty in parameters and predictions. Perhaps that uncertainty could be reduced if note was taken of ordering relationships which probably exists between the parameters in different watersheds by virtue of the geology, the land use, the rainfall which they receive. And that information about the ordering between the parameters of the same type in different watersheds can only be brought to bear in the inversion process if those watersheds are calibrated simultaneously. Now this requires estimation of a lot more parameters than if they're calibrated individually, but PEST doesn't care because of its sophisticated regularization functionality. The fact that a problem may be ill-posed is not a problem to it, but the problem will be less ill-posed if this extra information born of parameter regionalization relationships can be introduced to the inversion process through appropriately formulated Tikhonov relationships. This, in my opinion, presents a far better means of calculating surface water models than individual calibration of individual watersheds. Of course, we could even get more sophisticated. We can recognize that in each watershed there are different land uses and the same principles can be applied. Once again, PEST is not worried by a superfluity of parameters as long as proper regularization is introduced to the inversion process. And if that regularization can embody expert knowledge that expresses ordering relationships between parameters in different land uses and in different watersheds, then simultaneous calibration allows introduction of that information to the inversion process. This can promote parameter sensibility, a minimum error variance solution to the inverse problem of model calibration, reduction in the uncertainty of parameters and in predictions made by the model. And some of the utilities supplied with the surface water suite help in setup of inverse problems formulated in that way. Of equal importance is formulation of the objective function that must be minimized through calibration of a surface water model. One could ask, where is the information in a flow time series? Some of that information resides in the peaks at the peak of a wet season. Other information resides in the peaks early in a wet season. Some information resides in short-term recessions, some in long-term recessions, some in average flows. If we're going to get the most out of that flow time series, the most information out of that flow time series, that time series needs to be processed in ways that distill that information, that extract that information and place it into a multi-component objective function that is weighted for visibility of that information to promulgate maximum reduction in the uncertainties of parameters used by the model and hence maximum reduction in uncertainties of predictions made by the model. The flagship of the PEST surface water utilities is a program called TS-PROC. This was written with calibration in mind. TS-PROC stands for Time Series Processor. It undertakes processing of a flow time series in a variety of different ways which implement the principles that I was just talking about, that is, extracting the different types of information that reside in a flow time series and formulating an appropriate multi-component objective function. Not only does it extract that information from the flow time series, it automates setup of a PEST input dataset based on that multi-component objective function, thereby making this task as easy as possible. In conclusion, decision support modeling requires quantification of the uncertainties of decision-critical model predictions and assimilation of all available information in order to reduce those uncertainties as much as that information allows. This requires that models be used with appropriate dancing partners like PEST and other dancing partners supplied through the PEST suite. Not only does the PEST suite provide those dancing partners, It also provides utility software which assists in setting up complex inversion and uncertainty analyses processes, which allow us to get the most information out of expensive data and allows us to quantify uncertainties associated with decision-critical model prediction, and hence allows us to incorporate the vital element of risk assessment into the decision-making process. And that, after all, is the role of decision support environmental modelling. Thank you.